Thank you very much for the introduction and good morning from my side. My name is Kevin Kolpatzeck. I come from the Chair of Communication Systems at the University of Duisburg-Essen in the very western end of Germany. My lecture today is titled Compact and Mobile Terahertz Time-Domain Spectroscopy Systems Enabled by Semiconductor Laser Diodes, and I'm very happy to kind of kick off this lecture series with some hopefully useful fundamentals for you. So let's start with who am I and what do I do? So I'm currently postdoc at the Chair of Communication Systems here at the University of Duisburg-Essen. My personal background is mostly in communication engineering, RF engineering, and optoelectronics. So what you will realize is that my lecture today will be very much an engineer's perspective on terahertz. So for all the physicists in the audience, bear with me and don't cringe too much at my sometimes maybe somewhat simplified explanations. My current research interests are in mostly system concepts for mobile terahertz spectroscopy systems. Then large aspect is on optoelectronic terahertz radar, particularly a harmonic terahertz radar, and terahertz spectroscopy for non-destructive testing applications. I'm currently involved in 3 major research initiatives here in the region that I would like to quickly introduce to you because that may become interesting for you in the future. Namely, these are called Marie, Terahertz NRW, and 6GEM, and all 3 of them are located here in the so-called Ruhr Valley in the very western end of Germany. So this is the region that traditionally and historically is very much driven by heavy industry, but also hosts several very large universities that have a strong research focus on terahertz science and technology. So let me quickly introduce to you our collaborative research center, Marie, which is funded by the German Research Foundation. It has members from 5 universities and 2 Fraunhofer institutes with a total of 17 groups and a total of 27 PIs leading the individual projects. And what I would like to kind of decipher for you is that what our abbreviation Marie stands for. It is a material transceiver, as you see here. And the vision behind our CRC is to precisely and dynamically characterize and localize even moving materials in our daily surroundings using terahertz radar. Now, the grand vision is kind of shown in this sketch here. So the idea is that we use terahertz radar in like emergency scenarios to enable firefighters to get a general overview of in burning buildings inside, and also not only get like the general layout of the room, but also information about which materials are located in which locations. Then we have our research initiative Terahertz NRW, which is funded by the state of North Rhine-Westphalia here in West Germany. Again, we have many researchers involved, and here the focus is on medical technology and environmental monitoring. So here the general idea is to use terahertz radiation and terahertz spectroscopy for mostly for medical applications as well as for environmental monitoring. And finally, we have our research hub 6GEM, which is funded by the German Federal Ministry of Education and Research, which extends somewhat beyond the Ruhr Valley. Here, the focus is mostly on 6G communication systems, but there's also one key part focused on terahertz communications. So why am I telling you all of that? Well, the reason is, first of all, we always have open positions. We offer scholarships. There's plenty of opportunities for collaboration. So if you are interested in maybe working on terahertz science and technology in Germany, or particularly in our region, you're always welcome to contact me or maybe visit our websites. But I get back to that maybe at the end of the lecture once I've um, uh, given you some motivation to get involved in this field. So let me give you a quick outline of today's lecture. So what I'm going to start with is giving you a short introduction into what is terahertz radiation, what can we actually do with it. We will then look very closely at terahertz time domain spectroscopy, both in terms of the fundamentals as well as with the quick historical outline from where it started and where we're at right now. Then we will look very closely at terahertz spectroscopy systems that are driven by semiconductor lasers. So these can be very compact and mobile terahertz spectroscopy systems. And specifically what we're going to look at are two concepts that are called cross-correlation spectroscopy as well as ultra-high repetition rate terahertz time domain spectroscopy. We will take a deeper dive into the latter and then look at some current developments and applications. I will most likely, we are going to take a short break after about 2/3 of the lecture. So that is going to be roughly here before we take a deeper dive into ultra high repetition rate terahertz TDS. So if you have any questions, please collect them and I will try to answer some of the initial questions already in this short break here. Okay, so let's get started. So what is terahertz radiation and what can we do with it? So, well, actually, a good alternative name for terahertz radiation is submillimeter wave radiation because that actually describes very well what it is. It is electromagnetic radiation with wavelengths in the submillimeter wave range. The exact definition of what terahertz range actually encompasses somewhat varies, but it's roughly frequencies between 100 gigahertz and 10 terahertz, relating to wavelengths between 30 micron and 3 millimeters. So it is located between the infrared region and the microwave and millimeter wave regions. What makes terahertz radiation interesting is that it interacts very particular with matters. The interaction with most materials that we find in our everyday environment is quite mild. What I mean with mild is there is some interaction, but it's not that strong that it's completely absorbed or reflected. So that actually makes this interaction useful for practical applications. We have high absorption in water. It's more or less perfectly reflected by metal. And there are certain spectral absorption lines of water vapor and some gases in the terahertz range. And what's most important for say, biological applications that involve living creatures is that terahertz radiation is non-ionizing and thereby not harmful, for example, to the human body. So, since it's located between microwave and infrared waves, there's actually two different ways to look at it. Let's start by looking at it from the applications perspective. From the applications perspective, terahertz radiation kind of combines the best of both worlds. So best of the microwave and the infrared world. So terahertz radiation can look through and behind thin objects. We can use it thereby also to analyze multi-layer objects. It provides higher spatial resolution than microwave radiation. We can analyze the shape and material composition of objects, and it can be shaped and focused using reflective and refractive optics like we would do with light. On the other hand, from the technological standpoint, it kind of combines the worst of both worlds. So the frequency is kind of too high for electronics, but at the same time, too low for photonics, even though we will later see that that statement is not as simple as I have stated it here. So thereby we have this somewhat infamous terahertz gap, saying that in this terahertz, in this frequency region, we have a gap in terms of technological maturity as well as mostly transmit power. So what are the challenges here? First of all, we have a speed limit for electronic devices. We have a band gap limit at room temperature for laser devices. We have low transmit power. We have high free space and atmospheric loss due to the high frequency. And for example, when it comes to manufacturing, in terms of classical electronic devices, we have very tight manufacturing tolerances. So let's start by looking at some interesting applications. One somewhat famous industrial application that's already being in good use right now is for multi-layer thickness measurement. Let me just quickly turn on the laser pointer so I can also highlight some aspects. So here in this time domain trace of a multi-layer structure, you can see the reflections from several layers, and by analyzing the amplitudes and relative delays between these reflections, it is possible to determine the individual thicknesses of these layers. Also in the realm of non-destructive testing, you can use terahertz radiation to image internal structures of objects, for example, to differentiate authentic from counterfeit electronic chips. Then one very famous application is in security applications, particularly mail scanning, where we use terahertz radiation's property to be able to penetrate many materials, for example, paper, to kind of get a look inside objects like envelopes, also for like mail scanning and security applications. What you can see here, maybe I should highlight that this is a photograph from the outside. This photograph shows where the individual objects are located inside the envelope. Then we have a pure transmittance image as well as a time delay image. Then one very successful application of terahertz radiation right now is in art conservation. For example, what terahertz spectroscopy particularly was used for here is to detect delamination in old paintings. For example, what you could see here is these red dots indicate where delamination occurred before conservation effort, and then the blue dots indicate where delamination was detected after conservation work. Then in terms of medical applications, one thing that terahertz spectroscopy is often used for is for skin imaging, in particular for trying to detect skin cancer. And then finally, I would like to show work from our group in terms of 3D imaging using a synthetic aperture radar approach. So what you see here is a terahertz image of a 20-sided die. So this is about 2 centimeters in diameter, and you can very nicely see in this synthetic aperture radar image that was generated with the time domain spectroscopy systems, the letters or specifically numbers that are inscribed on the dice. So you can very nicely see this relief generated by the depth profile. Okay, let's move on. Now let's start by taking a closer look at one very well-known and very often used type of terahertz measurement system, which is terahertz time domain spectroscopy. So in a nutshell, this is what a time domain spectroscopy looks like a prototype drawing, like the most simple type of time domain spectrometer. So it consists of a femtosecond laser that emits optical pulses, typically nowadays in the 1550 nanometer range. These pulses have a pulse width of usually less than 100 femtoseconds, with a pulse repetition rate of roughly 100 megahertz. So one pulse every 10 nanoseconds. Now, these pulses are split into 2 branches. One feeds a transmitter, one feeds a receiver, and goes through an optical delay unit before it reaches the receiver. The transmitter is a biased photoconductive antenna that converts these infrared pulses into terahertz pulses. And then unbiased photoconductive antenna is used to sample the terahertz pulses with the same infrared pulses that are delayed with the optical delay unit. So this is in a nutshell. Let's go into it a little deeper now. Now, here you can see our femtosecond laser emitting these optical pulses, one pulse every, say, 10 nanoseconds. Now, when we look at it, what is actually driving the photoconductive antenna is the instantaneous optical power of the light wave hitting the photoconductive antenna. I'm denoting that with P opt Tx of T here. That is generating an electrical field in the terahertz domain that is denoted by E terahertz Tx of T here, which is then transmitted, for example, through a sample, and then received as E terahertz Rx of T. The photoconductive antenna on the receiver side, on the other hand, is driven by the same optical pulses, which are now delayed with an optical delay unit. So it depends now not only on the actual observation time, but also on the delay tau. The measured signal in time domain spectrometer is always the DC photocurrent, the detected photocurrent at the output of the receiver, which depends only on the delay of the optical delay unit. So looking at the individual components now, the photoconductive transmitter here is an electrically biased photoconductor that is located at the feeding point of a wideband antenna. At the same time, the photoconductive receiver is an unbiased photoconductor that is also located at the feeding point of a wideband antenna. And here, the conductors that are used on the transmitter side for biasing the photoconductor are used here as a low frequency output to output this DC measured photocurrent. So let me try to give an explanation of how the transmitter works and how the receiver works. Let me just say up front, I'm going to give an electrical engineer's perspective on that. So it's going to be a very simplified model. So it's probably going to make some physicists cringe, but I think it's going to be quite helpful for giving somewhat intuitive understanding of these system concepts. So the photoconductive material here is located at the feeding point of a strip line antenna. So this dark gray box here indicates the photoconductive material, and these lighter gray lines indicate the metallization on the chip. We have a bias voltage connected through electrical lines to the metallization, and thereby also to the photoconductor. So this photoconductive material is now biased with a bias voltage V bias. We have the incident light hitting the photoconductive material. So we have these kind of power pulses hitting the photoconductive material every 10 nanoseconds. And now this antenna radiates this electromagnetic wave in the terahertz frequency range. So now let's look at a simplified model of that in terms of a very simple equivalent circuit. Now our photoconductor can be represented as a conductivity whose conductivity depends on time. We have a current flowing through that conductivity and bias voltage applied to that time dependent resistor through an RF choke. So since these bias lines won't carry the terahertz wave, the terahertz wave is purely radiated into space, we can kind of represent these bias lines with an RF choke, meaning that any terahertz signal generated in this photoconductor will go only to the antenna, not to the bias source. So let's have a closer look at this. Now, because it is a photoconductor, the conductivity of the photoconductor is proportional to the instantaneous optical power hitting the photoconductive material. So that means that the conductivity here is following the shape of these optical pulses. Now, according to Ohm's law, that means that when we have a DC voltage applied to that, the current flowing through the conductivity will be proportional to that. Specifically, it's going to be the bias voltage times this time-dependent conductivity, meaning that the current flowing here will closely follow the shape of the optical pulses. And since this will now this current will consist spectrally of several different components. One is going to be a DC component, so like a component that is proportional to the average optical power. So it's going to be a DC current that will flow in this branch, and an AC current that is flowing through the antenna. Now, this AC current flowing through the antenna will then radiate a wave into free space. And this wave is going to be in the terahertz frequency range. It closely follows the shape of the optical pulse, with the difference that it's going to be proportional to the time derivative of the current flowing here. So this would be a very simplified explanation of the operating principle. Now let's have a look at the photoconductive receiver, where it gets slightly more interesting. Now here we do not apply bias voltage, but instead we use these electrical conductors here to measure the current that is generated in the photoconductive material. Here we have again the instantaneous optical power, these optical pulses radiating onto the photoconductive material represented by this time-dependent conductivity. We have our terahertz wave being received by this strip line antenna. And now what's happening here is that this received electric field induces a voltage that I've denoted by V terahertz of t here that is proportional to the incident electrical field. Now what's happening here is that we now have a time-dependent voltage being applied to the conductivity here. So the voltage is modulated by these terahertz pulses, and at the same time the conductivity is modulated by the optical pulse. Now, the current flowing will be simply the product of will be proportional to the product of the incident electric field in the terahertz range and the incident optical pulses. Now, again, we will get a fast current flow. However, only the average component of that, only the time average, will be measurable as a DC current here at the output. So we will get a measured photocurrent, which is proportional to the time average of this alternating current that is generated in the photoconductive material. Let's try to illustrate that a little bit. So let's try to illustrate this optical sampling technique. So what I've shown here in this little animation is E terahertz Rx of t. So this red line represents the electric field, the pulse that is being picked up by the receiver antenna. And in blue, you can see the optical pulse at the photoconductive receiver that is delayed by the optical delay unit. Then here on the lower plot, you will see this average photocurrent as we delay the optical pulse and shift it across the received terahertz pulse. So what we measure down here is proportional to the overlap between the red curve and the blue curve. And notably, what you can see is that since the optical pulse, denoted in blue here, is much shorter than the red pulse, this measured photocurrent closely follows the shape of the electrical field. So we're now using the optical pulses to sample the field that is received by the photoconductive receiver. So this was all simulation. Now let's look at some actual measurements. What I've shown here is a typical measured photocurrent at the output of the photoconductive receiver as a function of the delay that is introduced by the optical delay unit. So this shows a very typical delay range going from 0 to 150 picoseconds. So we have a total delay range of 150 picoseconds and received terahertz pulse here that is very similar to what I showed in the simulation. Now, when we introduce a sample, obviously the shape of that electric field will be altered. Now, what we can do is we can transform these measured photocurrents into the frequency domain using the Fourier transform, and we get what we would usually refer to as our terahertz spectrum. So in the terahertz spectrum, what you can very nicely see is that it drops off towards higher frequencies, and here the useful bandwidth would be roughly 4 terahertz, I would say. We can see these very distinct absorption lines here caused by water vapor in ambient air. And what's important now here is that according to the rules of the Fourier transform, specifically the discrete Fourier transform, the frequency resolution is now determined only or mostly by the length of the delay range, so by the length of our optical delay unit. Now you can see also in the spectrum that the spectral shape has been altered by introducing a sample into the terahertz path. And now what we can do is we can divide this spectrum with a sample by the spectrum without the sample, and thereby get here depicted in blue the magnitude of the transfer function of the sample. And if we also take the phase into account, the phase of the transfer function of the sample. Now we can use this information to evaluate our sample under test. Okay. Now look, after we finish this theoretical part, let's have a little bit of a historical overview of terahertz time domain spectroscopy. So basically the fundamental requisites to be able to construct time domain spectroscopy systems were laid in the 1970s when passive mode locking was first introduced with introducing pulse widths of approximately 1.5 picoseconds. Then in the early 1980s, this pulse width was reduced to 90 femtoseconds, which is already short enough for terahertz generation. And then in 1981, for the first time, so-called photoconductive switch, which is basically photoconductive antenna, was used to generate microwave pulses, basically using the exact concept that I already introduced to you. Then in 1984, the exact concept that I just introduced to you was used to both generate and detect terahertz pulses with photoconductive antennas. In that case, the photoconductive antennas were placed on two sides of an insulating slab. So the pulses were just transmitted through that insulating slab by Austin and co-workers. And then in 1988, by Fattinger and Grishkowski, the first demonstration of using such a system also in the reflection geometry was introduced. And what's interesting about that work is that in 1988, it was the first time that such a system was also connected with the term terahertz. And then 1 year later, these terahertz pulses were also transmitted over a distance of 1 meter. And it was for the first time introduced that also optics can be used to manipulate terahertz. radiation. So I would say that 1989 approximately was when the first system that looks very similar to a nowadays terahertz time domain spectroscopy system was introduced. Now, how did we get from like first experimental systems to systems that can actually also be used for industrial applications? So the first demonstrations were, well, basically room-sized using dye lasers, and they mostly used lasers operating in the 1850 nanometer range, and were mostly using photoconductive antennas based on low-temperature chrome gallium arsenide. Then the first somewhat, let's say, compact in meaning table size TDS system was introduced in 93 using a titanium sapphire mode lock laser. And then very importantly, in the next year, it was for the first time demonstrated that you can also construct photoconductive material that is sensitive in the 1550 nanometer range, so in the typical telecom band. And then in 2008, for the first time, an all-fiber Terahertz TDS system was demonstrated that was driven by a fiber laser. And since then, it was mostly technological advances that helped increase the transmit power of the transmitters and the sensitivity of the photoconductive receivers. But since 2008, basically, we have quite compact and basically plug and play terahertz TDS systems. So here I've shown you two examples of commercially available TDS systems. So as you can see, they are fully fiber coupled. They are basically plug and play. They operate in the 1550 nanometer telecom band and use mode lock fiber lasers at the light source. With a pulse with, as I said, of usually less than 100 femtoseconds and a pulse repetition rate of around about 100 megahertz. The bandwidth these systems can achieve nowadays is more than 5 terahertz with an impressive peak dynamic range of more than 100 dB. Now, we have to kind of separate it now is in the terms of the spectral update rate. So for conventional systems like the ones that I showed to you using optical delay unit, we get spectral update rates of several spectra per second. However, there are also concepts that do without an optical delay unit where we can get update rates of several 100 spectra per second. So now the question is, why? Well, since this technology is already quite mature, and we can see that we achieve this impressive specifications. So what is actually holding back more widespread industrial use and also use in mobile applications? Well, comes down partly to the system cost, since all of these systems cost way more than 50,000 euros. Which is mostly due to the use of a fiber laser and a highly precise optical delay unit. And even the most compact systems still require 3 height units in a 19-inch rack and have a system weight of more than 10 kilograms, which kind of hinders many mobile applications. Then these systems are mechanically still quite sensitive due to the mechanical optical delay units. And most importantly, there's very little potential for actually constructing a truly integrated system. First of all, it's because the fiber laser cannot be integrated on a chip. Then we have a lot of technological heterogeneity, meaning that there's different kinds of technology involved in the system. And we have this physically long free space optical delay unit. Now, one aspect where there's very active work on finding solutions actually is by trying to find alternative light sources. So when we look at alternative light sources, which properties should they fulfill? Well, first of all, it would be nice if it would be monolithically integrated. It should be light source that is, if electrically pumped, which would be very convenient if the optical output power of that light source is already high enough without amplification. we would like to operate that source in the 1550 nanometer band, and hopefully the system bandwidth and dynamic range that we can achieve with that late source is actually comparable to state-of-the-art TDS systems. So with that, we get to the second part of the lecture where we look at terahertz spectroscopy systems that are driven by semiconductor lasers. Let's start by looking at a concept called terahertz cross-correlation spectroscopy. In 1997, it was demonstrated that you can generate an RF comp by driving a photoconductive antenna with a very low cost, off-the-shelf, simple multimode laser diode. Then 2 years later, it was demonstrated that such a source can also be used for spectroscopy. What they've done there is they've generated an RF comb um, by driving a photoconductive antenna with a multimode laser diode, and then used a bolometer together with an interferometer to receive that radiation. Then in 1999, a group in Japan demonstrated that it is also possible to drive a very conventional TDS system with such a multimode laser diode. And what they found, now it gets interesting, is that first of all, the detected photocurrent in the delay domain is now periodic with a repetition rate of the multimode laser diode, which in that case was about 52 gigahertz. And even though the laser modes randomly change their amplitude and phases, so the light intensity fluctuates rapidly, still we could measure a stable DC photocurrent at the output of the photoconductive receiver. And what they found is that at that point, you're no longer measuring the convolution between the optical pulse and the terahertz pulse, but what you're actually measuring is the cross correlation between the optical, let's say, optical noise and the terahertz noise at the receiver. And for that, we'll also create a small animation. So what you can see here again in red is the terahertz electric field that is received by the photoconductive receiver, and the incident and delayed light also incident on the photoconductive receiver. What you can see that they're both kind of noise-like, but we can still see a little bit of periodicity here. Now, in the lower plot, you will see the detected photocurrent at the output as a function of the delay that is introduced by the optical delay unit. Now let's observe that evolve over time. We can see a first pulse here, another pulse. We can see that the distance between these two pulses is 20 picoseconds, which is the reciprocal of the laser's repetition rate. Now, what's interesting here is that the pulse we measure here is actually very similar in shape to what we observed with the conventional TDS system. However, what we see is that now we don't have one single pulse, but we actually have multiple pulses, and the distance between these pulses is determined by the cavity length of the laser diode. But what you can also see is that the amplitude of these pulses decays as we move away from the 0 point of the system, basically as the correlation between the optical signal and the terahertz signal also decays as we move away from the 0 point. So when the optical light and the terahertz light are very close in time, they are also very highly correlated, leading to a high pulse amplitude here in the middle. Okay, don't need to watch that again. Then quite recently in 2017. Such a system was for the first time demonstrated also operating at 1550 nanometer. In that case, they used state-of-the-art transmitter and receiver modules and achieved a bandwidth of about 1.5 terahertz with a peak dynamic range of 60 dB. And here you can see the received terahertz pulses, which look very similar to our simulation. And after transformation into the frequency domain, we now get discrete spectral lines up to a frequency of about 1.5 terahertz. And you can see that the spacing between these lines is determined by the repetition rate of our laser. Now, and since we could already see that even when our light source basically emits, let's call it periodic noise, we can still use that for terahertz spectroscopy. An alternative approach was demonstrated in 2019 by Malta and co-workers, where they actually took it a step further and replaced the multimode laser diode with the superluminescent diode. So the superluminescent diode doesn't have a laser cavity anymore, so the laser spectrum doesn't have a mode structure anymore. So what we have is a very smooth spectrum with an optical bandwidth of with a very wide optical bandwidth of about 5.7 terahertz. And when they use that to drive the terahertz spectrometer, what they get was a single pulse in the time domain, creating a continuous terahertz spectrum up to 1.7 terahertz. Now again, little simulation. Now you can see that because we do not have a mode structure in the laser spectrum anymore, we no longer have a periodic signal. So we basically have optical noise and terahertz noise that we're cross-correlating now. And as we observe the detected photocurrent evolve, we can now see that in the middle of the delay range, we get one distinct pulse, which again is very similar to what we would observe in a conventional time domain spectrometer. So now, obviously, such a system can be much more compact. Now, the light source is simply a semiconductor laser, which is also very much lower in cost compared to fiber laser. But what are the disadvantages? First of all, the terahertz bandwidth is lower than in a conventional system because the optical bandwidth is also lower. And also the dynamic range is much lower because the mixing efficiency is way lower when we're cross-correlating noise instead of mixing truly periodic signals with each other. So one possible solution is to find something that's kind of in the middle between the two systems. And the system that I will introduce to you in the next part of the lecture actually uses monolithic mode-locked laser diodes. But before I do that, let's take a very short break because I think this is perfect time to do that. So I can quickly catch a breath, and you can, if you have any questions, use the chance to ask those. Yeah, perfect. Thank you. So I saw that there's already 6 questions now. That's awesome. Let me just go through them in the order in which they arrived. So the first question is, did I understand correctly that the sampling pulse allows to get better FFT resolution compared to a non-sampled one? Mm, let me try to rephrase that question a little bit. So the basic operating principle here is that we use the optical pulse to sample the terahertz pulse. So that is not directly related to the FFT resolution yet. But what is a fact, and actually we can see that with a very nice example later on in the lecture, is that the theoretical frequency resolution limit is determined by the repetition rate of the laser, whereas the practical limit in most cases is the length of our optical delay unit. So the practical frequency resolution limit is always in a conventional system is the length of the optical delay unit. But we can see, and I can already show you that now, in a system that is driven by a multimode laser diode. Here, we see that we now get discrete spectral components here. And we're going to get exactly these spectral components no matter how long our optical delay unit is. So in that case, our frequency resolution of the system is determined by the mode spacing, or is equal to the mode spacing of the multimode laser diode. That would be the hopefully answer your question. Then the second question is, where does the correlation between the optical noise and the terahertz noise come from? Excellent question. I think that that's a point that I kind of skipped over, because, well, the reason is that when we look at this setup again, let me try to find a good place to show it. Let's go way back here. Now assume that this laser source now is not a femtosecond laser anymore, but is actually our optical noise source. Now it's actually the same noise is generating the terahertz radiation as we use for detection here. That means that the terahertz noise is correlated to the optical noise at the transmitter, which is obviously also correlated to the optical noise at the receiver. The only difference being the delay introduced by the optical delay unit. So that's where the correlation comes from. It's because the terahertz noise is actually generated by the exact same optical noise. Then the next question was regarding the last animation that I showed. Must be this one. This one. The question is, what is the correlation between E of t at 500 picoseconds and I of t at 50 picoseconds? I think I know where the question is coming from. I think my figure is kind of irritating here because of the different time axes that I'm using here. Here, 50 picoseconds on the delay axis is actually just the middle point of our delay range. So 50 picoseconds here would be the point where the terahertz pulse and the optical pulse, or in this case, the terahertz noise and the optical noise perfectly overlap. What that would mean is in the block diagram, let me try to show that here. In the block diagram, what that would mean is that at that exact point, the delay that is introduced by the optical delay unit is exactly equal to the delay in free space between the transmitter and the receiver. So 50 picoseconds in this example would be the delay between the transmitter and receiver. So at this point of 50 picoseconds delay, we have a perfect overlap between the optical and the terahertz noise. I hope that answered your question. Then I have a slightly longer question. My work was using on LED to highly resolve an object up to a micron level. How can I improve this work for my PhD to use terahertz? To be honest, I cannot give you a perfect answer to that. I would need to look into that in more detail. But what I would say at this point is that using LED is somewhat similar to using a superluminescent diode. But from what I would say is that since the optical bandwidth is way lower, the achievable terahertz bandwidth would also be much lower. So to be honest, I need to look into that. So if you would just shoot me an email, maybe I could give you a more honest answer in a few days. Then the next question is the bandwidth of the Terahertz CCS system should depend on the bandwidth of the optical noise. Am I right? Yes, you're right. Yeah, yeah, absolutely. It depends on the bandwidth of the optical noise as well as the overall low pass behavior of our transmitter and receiver. And then the last question up to this point is what are the pros and cons of using PCAs compared to using telluride crystals and TDS systems? I guess probably I'm not the best one to answer that question, but at least from my perspective, what I would say is that with the zinc telluride crystals, you can generate higher transmit power and also way higher bandwidths. But from a practical standpoint, the advantage of PCAs is obviously that they can be fully fiber coupled. So for say industrial applications, it's way easier to use PCAs because you can just take them with a fiber attached and place them at your object under test. And now I got another question. A pulse laser and the PCA are capable of generating a Terahertz frequency comb. Is that also possible with a mode locked laser diode? That exactly will be the second part of this lecture. So thanks for the introduction. All right, so let's move on. So far we have looked at using mode-locked fiber lasers for TDS, and we've looked at optical noise sources, specifically multimode laser diodes and superluminescent diodes for something that's closely resembles TDS, which in that case is called cross-correlation spectroscopy. Now the idea was to find something in the middle. And the idea here is to use a semiconductor light source that is also mode locked. So what we're looking at now are so-called mode locked laser diodes. And in 2017, it was first demonstrated to use a monolithic mode locked laser diodes to drive a conventional TDS system. In that case, it was a single section quantum dash mode locked laser diode with a repetition rate of 41 gigahertz. And with that, they were able to demonstrate a terahertz bandwidth of roughly 600 gigahertz. Here on the right, you can see that the detected photocurrent is now periodic with a repetition rate that is equal to the mode spacing of the laser. And when we transform that into the frequency domain, we now get a terahertz spectrum with discrete spectral lines that are spaced by the repetition rate of the laser. Now, what's interesting here, when we compare this to the previous plots, is now because the light emitted by the mode-locked laser diode is no more, let's say, periodic noise, but it's actually a truly periodic signal. Now, the amplitude of these pulses in the delay domain no longer decays towards the as we move away from the 0 point. So the amplitude of these pulses stays more or less the same. And then last year in our group, through several improvements to this approach, we were actually able to demonstrate a peak signal to noise ratio of up to 133 dB using a two-section monolithic laser diode with a repetition rate of about 50 gigahertz. But we'll see much more on that at the very end of this lecture. Now, what do these systems actually look like now? So I have two photographs here. The one on the right is what is our current compact mobile demonstrator system. So we have all the required components. That is the light source. That is the optical delay units, all the fiber optics, electronics, all in this somewhat compact housing. We have our transmitter here and our receiver here. And then on the other hand, we have our high performance experimental system that was used for the 133 dB experiment here on the left. Here you can see the mode-locked laser diode, and here the optical delay unit, as well as several fiber optic components. Now let's take a deeper dive into this system concept. So if we look at the original measured signal, the measured signal again is the DC photocurrent at the output of the photocondactive receiver as a function of the delay introduced by the optical delay unit. Now, what's important now is that with the mode-locked laser diode, with a high repetition rate, the photocurrent that we measure is now periodic, as we've already seen, with the repetition rate of the laser. And now when we see that, as you can see, we have one period of this periodic photocurrent recorded here. Now, when we introduce a sample into the Terahertz path, obviously the change of that photocurrent changes. But what's important now, when we now transform this into the frequency domain, the frequency resolution is now no longer determined by the length of the optical delay unit, but it's actually now determined by the repetition rate of the laser. So if we have a laser with, say, a repetition rate of 50 gigahertz, 50 gigahertz are going to be our frequency resolution. Now again, we can divide the spectrum with a sample by the spectrum without the sample and get the transfer function of the sample. And what we now see is that this transfer function is actually the same transfer function that we measured with the conventional system, but now it's just sampled in the frequency domain at integer multiples of the laser's repetition rate. So what are the consequences of this very high repetition rate of several 10 gigahertz now? Well, first of all, as we've already seen, the photocurrent is now periodic with the repetition rate of the laser. So it's, for example, with 50 gigahertz repetition rate, it's periodic every 20 picoseconds. It doesn't actually look like a pulse anymore because the pulse duration and the pulse repetition period are actually very similar to each other. The peak optical power is very low, which means that we have a low pulse energy. And as a consequence of that, we have observed that it is actually better to use an antenna integrated photodiode as the transmitter compared to using a photoconductive antenna as the transmitter. The receiver should still be photoconductive antenna. Well, what are the disadvantages and advantages? Well, first of all, disadvantages. Well, as we've seen here, this is difficult to evaluate in the time domain. So because we do not actually have distinct parts anymore, it's very difficult to evaluate that signal by eye by looking at it in the time domain. Now, our spectral resolution is obviously limited, and we have what we call delay ambiguity. So if we observe reflection at a certain distance, we will observe the exact same reflection if it's located more than one repetition period away. In terms of advantages, we now can process these signals very efficiently, as we will later see. The optical delay unit can be much shorter because it only needs to encompass one repetition period of the laser. And what's very interesting now is that no matter how long our optical delay unit is, we will always be able to observe a pulse. So we no longer need to align the optical pulse with the terahertz pulse because both the terahertz signal and the optical signal are periodic. We will always have one repetition of each signal overlapping with each other in the range of our optical delay unit. Now, what I would like to briefly introduce to you is a system theoretical model for this approach. So what we want to do now is try to derive a as simple as possible mathematical model for this system. So we have our light source here. We need to compensate the chirp of the laser pulse and now get our, again, our low pass filtered instantaneous optical power. We split that up into branches and now we'll characterize the Terahertz system here, which involves the transmitter, the receiver, and the terahertz path by combined transfer function h terahertz. Now, what we need to start with is looking at the optical fields. So this is the electric field basically in the optical fiber. It consists of several spectral components, several harmonic components. The frequencies of these harmonic components are equal to the center frequency of the laser comb plus integer multiples of the laser's repetition rate. So these are actually just the individual laser modes. Each laser mode is characterized by its amplitude and its spectral phase. Now, what we can calculate from this optical field is the low pass filtered version of the instantaneous optical power. So we can see that we have a component that doesn't depend on time. So this is basically the average power component. And we have spectral components that have frequencies that are integer multiples of the laser's repetition rate. Now, to be able to calculate our detected photocurrent, which is actually the quantity that we want to measure, we need to make a few assumptions. Well, the first assumption is that we assume that the transmitter and the receiver both respond linearly to the instantaneous optical power. Then we assume that the terahertz channel can be described as a linear and time invariant channel. Because in that case, the entire terahertz system can be simply represented as a transfer function that depends only on the angular frequency. And we can thereby calculate the detected photocurrent. Now, so this equation looks kind of daunting, but we can actually break that down and see that it's actually very simple. So we have our detected photocurrent, which depends only on the delay introduced by the optical delay unit. Now we can see in the delay domain that we have several sine functions. We have actually a sum of sine functions. The individual frequencies of the sine functions are integer multiples of the laser's repetition rate. And now when we look at the amplitudes and phases of these sine functions, we can see that the phase is only determined by the phase of the transfer function of the terahertz signal at that frequency, whereas the amplitude of the individual spectral components is the product of the magnitude of the transfer function at that frequency multiplied with an amplitude factor AM. And what's important now is that these amplitude factors AM are now determined by the shape of the laser spectrum of the mode-lock laser diode. Specifically, they depend both on the amplitude spectrum as well as the phase spectrum of the mode-lock laser diode. Now, but what's important now is that as long as the light source doesn't change, this is just a very simple linear factor that goes into the equation. Now, we can do a similar calculation to calculate the intensity autocorrelation of the output signal of the mode-lock laser diode. And we find, and the interesting thing now is that we find that the exact same spectral amplitudes, AM, that we calculated here also appear in the intensity autocorrelation of the output signal of the mode-lock laser diode. So this is what we would measure with a second harmonic generation autocorrelator. And what that means now is that the detected photocurrent, so that's the measured signal at the output of the terahertz spectrometer, is simply consists of spectral components at integer multiples of the laser's repetition rate that are weighted by the autocorrelation spectral amplitudes of the mode-locked laser diode's output signal. So what we wanted to do now is to actually experimentally prove that these relationships are actually correct. So what we did is several experiments. First of all, we measured the optical spectrum of the laser diode, both in terms of amplitude and phase, using a simple optical spectrum analyzer as well as a stepped heterodyne method, and used the optical amplitude and phase spectrum to calculate the intensity autocorrelation. Now we compared that to the intensity autocorrelation that we can directly measure with an autocorrelator at the output of the laser diode. As you can see here, in red, you see the intensity autocorrelation pulse that we calculate from the optical spectrum, and in blue you can see the measured intensity autocorrelation, and here the same when we transform it into the frequency domain, and obviously there is a very good match. Now, in the next step, what we did is we measured the transfer function of the Terahertz system with a frequency domain spectrometer, and then calculated the Terahertz spectrum based on our optical spectrum and the transfer function, and also based on the transfer function and the intensity autocorrelation amplitude that we get from our measured intensity autocorrelation. Now the question is, does that actually match the spectrum that we measure directly with our Terahertz spectrometer? And again, you can see there's a very good match across the entire frequency range from 50 gigahertz up to about 1.3 terahertz. Here in blue, you see our measured terahertz spectrum. In red, you can see the terahertz spectrum that we have calculated from the optical spectrum of the laser diode. And in yellow, you see the spectrum that we calculate from the intensity autocorrelation of the laser diode. Now, we've already introduced one way to construct a lower cost system, which is replacing the fiber laser with a laser diode. Now, to address another challenge is to now go ahead and replace this somewhat high cost optical delay unit with something cheaper. And in our system, we used a relatively cheap off-the-shelf optical delay unit from OZ Optics. And the way we operate that in our system to get as high measurement speed as possible is to just let it run back and forth at basically uncontrolled with the highest speed possible. And what we can see now is because we operate that in an uncontrolled way, just letting it run forward and backward as fast as possible, we're introducing a delay error now. So that means that the delay that is introduced by the optical delay unit is no longer the delay that we assume it to be. So here on the horizontal axis, you can see the assumed delay, and here on the vertical axis, you can see the deviation from that assumed delay. So obviously, we have an acceleration phase where the delay lags behind the assumed delay, and a deceleration phase where the delay leads the assumed delay. But on top of that, we also have some ripple here that is caused by the spindle of the linear motor. So what are the consequences of these delay errors? Well, first of all, our time and phase accuracy are reduced, which means that averaging will perform very poorly, and also the spectrum will appear to be distorted, what we can kind of see here. So we would assume very sharp spectral lines here, but we can see that these are actually widened because of these delay errors. So what can we do about that? Well, one possibility was actually introduced by Daniel Malta and his co-workers in 2017, where they basically polarization multiplexed um, the the laser signal from a continuous wave laser through the time domain spectrometer to basically get a Mach-Sender interferometer constructed around the optical delay unit. In that case, they got an interferogram here at the output of a photodiode that was cosine shaped. Now, what they did was they used that interferogram as a reference signal to reconstruct their delay axis. However, they could only like fine-tune the delay axis using the relative information that they got from them, but didn't have an absolute time reference. Now, we looked at that concept very closely and thought that maybe with our mode lock laser diode, we can actually do it a lot simpler. So what we did was the following. Here you have our standard ultra-high repetition rate Terahertz TDS system. And all we did now is we introduced two optical splitters into the path. So we split off a little bit of the optical signal going to the transmitter and a little bit of the optical signal going to the receiver and combined them in a 50-50 fiber coupler and fed that combined signal into a balanced photodetector. Now we could record the photocurrent generated by that photodetector as a reference signal and compare that to our received photocurrent. As you can see now, we've basically constructed a Mach-Sender interferometer around the optical delay unit. So this concept is actually very similar to what Daniel Malta and his co-workers presented, but we're now not relying on an additional light source, but we're actually using the light from the mode lock laser light itself as a reference signal. Now, when we calculate the interferogram that is introduced here, it consists of spectral components that, again, are integer multiples of the laser's repetition rate offset by the center frequency of the laser spectrum. So what do the signals look like that we measure with the oscilloscope right now? We measure two signals. One is the periodic interferometer signal depicted in blue here, and in red, our periodic detected photocurrent. You see, they both have the exact same periodicity determined by the repetition rate of the laser. And when we look at this very closely now, we can see that the interferogram has a periodic envelope and within that envelope, we actually have a high frequency oscillation that has a frequency that is determined by the center frequency of the laser diode. So how can we use these signals? Well, actually, it's very simple. The first thing we do is we cut out a little part of that measured signal and determine the envelope of the interferometer signal. So we have the envelope in yellow here. Now we locate two adjacent maxima of that envelope and simply split the measured signals between these maxima. When we do that, what we basically do is we cut out exactly one period of our periodic signals. So we cut out exactly one period of our periodic terahertz photocurrents. The next step will then, so this would be somewhat like a synchronization step. In the next step, we can then fine tune, so correct our delay axis. So to do that, we find the locations of the zeros of the interferogram, so of this internal high frequency oscillation. And all we need to do now is we resample the terahertz signal onto the locations of the zeros of the interferogram. So the assumption here we make here is that this interferogram should be a periodic signal. So the distances between between the zeros of the interferogram should be equidistant. And if they're not, this is actually an error that is introduced only by the optical delay unit. So by resampling at these locations, we are perfectly correcting any errors introduced by the optical delay unit. And with that, I will just very briefly, and I think we're perfect in time for that, look at some current developments and applications. Well, here again, I'm showing you the results from our from last year's paper, where we use this approach to correct the delay axis and then average over a very long time to get our peak dynamic range of 133 dB at 100 gigahertz with a useful spectral range of about 1.5 terahertz. So what you can see here very nicely is that in red, we get our raw spectrum without any correction of the delay axis. In blue, you see the spectrum that we would predict from the optical spectrum and the transfer function of the terahertz signal, terahertz system. And then in yellow, we get our corrected spectrum. And you see that there's actually now, after correction, a very nice match between the corrected spectrum and the predicted spectrum. Now we use the system to perform several different measurements. One was in 2021, where we performed transmission measurements on cling film. So these layers of, so we basically stacked layers of cling film. Each layer has a thickness of, I think it's about 15 micron. And now when we measure the impulse response by referencing these two as a measurement without the cling film in the terahertz path, now in the impulse response, you can very clearly differentiate these individual layers. So this was kind of to demonstrate the time resolution that we can achieve with the synchronization approach. Then we've performed some transmission measurements on a dielectric filter. And here this is actually the example that I showed you in the very beginning of the lecture. In blue, you can see the spectrum that we acquired with a conventional commercially available TDS system compared to the spectrum that we measure with our ultra-high repetition rate system. And the important aspect now, it's basically identical. It's just that we now sample the spectrum with a high frequency resolution at integer multiples of the laser's repetition rate. And then finally, the last application that I wanted to show you, these are some very recent results, is we performed measurements in reflection mode on dielectric samples. Specifically, this was plexiglass with several different thicknesses. And what you can see here now is the transfer function that we measured with our ultra-high repetition rate system. And what we now did is we developed a mathematical model for the transfer function that we should expect from such a measurement based on an ABCD matrix multi-layer model. Then we used a genetic algorithm to fit the model parameters to our measured spectrum. And we could, using that, we were able to determine the refractive index and the thickness of the sample simultaneously. And what we were particularly interested in is what is actually the consequence of the ultra-high repetition rate of our system. And what we found is that in order to determine the thickness and refractive index of optically thick samples, all we need to know is a rough estimate of the thickness and refractive index of the sample. Specifically, what we need to know is we need to roughly know the product of refractive index and sample to within the speed of light divided by 4 repetition rates of the mode lock laser diodes. So with that, let me just give some concluding remarks. So first of all, Terahertz TDS has been around for approximately 35 years now. It has found many applications. Modern fiber-based, laser-based systems are convenient solutions. They're basically plug and play with impressive bandwidth and dynamic range, but still they're still somewhat bulky and expensive. And one alternative would maybe systems based on semiconductor lasers. Different approaches that I've shown you now are using multimode laser diodes, superluminescent diodes, or mode lock laser diodes. And recently we have observed huge improvements in terms of dynamic range and measurement speed, but there's still plenty of work to be done. And well, what we found is that probably the best solutions and sometimes unusual solutions is that are generated when people from different fields are working together. So if we're physicists and engineers, people working on signal processing are all throwing all their knowledge into a hat to kind of work together and develop new solutions. So I hope with that I've sparked some interest in our work on terahertz science and technology. And if you may be interested in working on that field, maybe also in this particular region, we are always happy to welcome you. And feel free to visit our website, get in touch with me, and we'll be very happy to set you up with someone who may be working on the exact field that you are interested in. With that, I would like to thank all of you for your interest. And now let's use the remaining time for a fruitful discussion on the topic. Well, thank you very much.
Thank you, Kevin, for an absolutely beautiful lecture. Yeah, so you are all very, very welcome to input your questions into the Q&A section. Also, if you'd like to write a few words to the speaker. So yeah, we're awaiting your questions. There is actually one already there if you'd like to answer.
Yeah, I'm looking at that right now. The question that is in the chat is, what in case if the sample observed by the terahertz possesses longer impulse response than the repetition period of the mode lock laser diode? That is actually an excellent question, and I'm thinking about the best possible answer right now. When you say longer impulse response, that can actually mean different things. So longer impulse response can, for example, mean that it just decays very slowly.
Kevin, I think what they mean is when you have one pulse and here comes another pulse after the round trip time, but the impulse response of your sample has not decayed yet. So you have some overlap between the measured pulse from a second round trip with the response of your sample and what distortion or artifacts that produces. It's not my question, but I can infer.
Thanks for clearing that out. I think yes, I believe that that's what it means. And exactly, basically what you said is already part of the answer. So yes, these pulses, they're just gonna kind of blend into each other. But what I should maybe mention here, let me just try to find a suitable slide for that. Actually, this one is already useful. These pulses basically blending into each other is just a natural property that we observe in any case because the repetition rate is so high. But specifically when the sample has a very long impulse response, this effect will be, well, obviously will be very pronounced. But this is exactly what I mentioned before, is that evaluating these time domain signals in the time domain is close to impossible. But when we transform this into the frequency domain, let me show if I can try to find something suitable to show that. Just give me a second.
I mean, you already mentioned that it will be undersampled, so you will see just a small fraction of the feature because the long range implies high spectral resolution. So it will produce a narrow dip. You would probe just one point of the dip, you will miss of the rest. So it's more or less an aliasing problem.
Exactly. It's this is important. It's an aliasing problem in the frequency domain. So we are undersampling the transfer. So what we're doing, we are undersampling the transfer function in the frequency domain, thereby introducing a periodicity in the time domain that is not actually there. So this is what's going to happen. And this is actually what I showed on the very end of the lecture. Let me try to fast forward there. Yes, here. This actually, for example, for this application of performing reflection measurements on the sample, the effect is that the transfer function that we will measure will be in a sense periodic with the thickness of the sample. So we need to roughly know the thickness of the optical thickness of the samples beforehand. So I hope that answered your question. So let me read the second question. When you calculated the transfer function by dividing different spectra, what physics can you learn from data, or what can you interpret from the data? And the blue and red curves showed from the sample measurements. Also, thank you for the great talk. Let me try to go to that slide. I believe that must be, was it this one? Let's just assume it's this one. So in this case, this was actually a transmission filter that my colleague Tobias Kubicek designed kind of as a frequency reference for our lab. So it's basically like a periodic structure consisting of multiple Fabry-Perot resonators placed next to each other, kind of in a periodic repetition of a certain unit cell. And what we simply did here is use the Terahertz spectrometer to verify that the transfer function of that sample of this filter actually matches the design that he did in a electromagnetic full wave solver. So in this terms, it's not actually too much of physics that we learned. It was more of a verification of a filter's transfer function. I hope that answered your question.
I think we can also talk about gas or solid spectroscopy, whereby measuring the absorption or the dispersion spectrum, you can learn where the resonances are and how they relate to the different intramolecular motion of like a whole crystal lattice. So there's a lot of physics there, but it's mostly, in the case of gases, it's a rotational, purely rotational spectra. So the physics of terahertz from a spectroscopy standpoint is slightly different from that of the electrical engineering perspective. And there's a whole bunch of, for water vapor, for alcohols, for some nervous agents, they have unique optical spectra. So there's a lot of physics, and it mostly relates to some smaller energy rotations, which you didn't talk about, but of course they will come up, you know, sooner or later.
I hope so.
Yeah.
So there's plenty of talks to follow this one.
Yeah.
But maybe one thing I should mention is that the particular type of system I just showed you, these ultra high repetition rates, is not probably the worst kind of system for these kind of applications. So when it comes to observing very narrow spectral features, obviously what you need is a high spectral resolution. So in these cases, you should definitely use a conventional time domain spectrometer, or maybe even a frequency domain spectroscopy system instead of these systems driven by mode-lock laser diodes. Then another question is, what do you mean by chirp compensation in ultra-high repetition rate Terahertz TDS systems and how it's realized? Excellent question. Let me go to this slide. Is it this one? I think this is probably the best place to answer it. One property of the laser diodes that we used here is that they emit very strongly chirp pulses. In fact, the chirp is so strong that basically we are only emitting one frequency at a time. So basically within one repetition period of the laser, we're chirping across the entire spectrum. So we have very strongly chirp pulses. And as we've seen here, let me try to find a suitable slide. Actually, I think that would be this one. Here. What we find is that we get the highest terahertz spectral amplitudes only for the case of an unchirped laser pulse. So only if the phase spectrum is either constant across the spectrum or linear across the laser spectrum will we get the highest terahertz pulse amplitudes. Because only in that case will these cosine functions here actually overlap constructively. So we need to, so it's definitely necessary to compensate that chirp. And here we have actually, we're in a very lucky spot. Let me show this first here. Because the sign of the anomalous dispersion of simple single mode fiber is actually the exact opposite compared to the sign of the laser chirp. So we can actually use just a very simple section of single mode fiber to compensate the laser chirp almost perfectly. So all we need to do is find the suitable length. And actually, this is kind of interesting to show here. When we look at this demonstrator system, this fiber that's wound around here, it's approximately 60 meters of fiber are used to compensate the pulse chirp. So in this case, it's very simple to just use a suitable section of single mode fiber. And then another question is, can you control the polarization of terahertz radiation? Yes. Yes, we can. And actually, there's different ways to do it. The first step to do that is obviously through the antenna that we use. So the first step to control the polarization is by controlling the polarization of the antenna. And in a second step, because most antennas will, well, primarily produce one polarization, one linear polarization usually, but also a little bit of cross polarization. What you can still do is add an external, for example, wire grid polarizer to clean up the remaining bit of cross polarization. Yeah. Let me show you an example. Let me try to find something suitable. Oh, yeah, should have shown this one. For example, these transmit and receiver modules from Fraunhofer HHI in Berlin that we are using, they are based on bow tie antennas, which produce primarily linear polarization. And in that case, you can mostly adjust the polarization by simply rotating the module in the mount. I hope that answered your question sufficiently.
Okay, we've reached 11 o'clock. We have one last question. Okay, let's allow it. Let's allow the one last question and then we're gonna wrap it up.
Yeah. But to be honest, it's a very relevant question. So I'm happy to answer that. So do you detect saturation of system or is it not relevant? The honest answer is we believe that we have not observed any saturation, and we've been believing that for a very long time, but we're just now observing that it may not actually be true because we may actually be observing saturation in the photoconductor, no, actually in the photodiode transmitter. And The problem when we have saturation is that in that case, we can no longer model the system as a linear system. So this is a very relevant question. And the answer is we are actually looking into that as we're speaking.
Okay. And with this, we'd like to conclude today's lecture. Thank you very, very much, Kevin, for this brilliant introduction. And next week, actually, it's going to be Łukasz Staczewski who will give a talk on ultra-broadband terahertz spectroscopy with organic nonlinear crystals.
Yes,
So
thank you,
again,
Kevin, for the introduction, because I will strongly rely on the concepts that you introduced, because it will be an expansion or replacement of the antennas with the crystals.
Awesome. Thank you very much. And thank you, everyone, for your interest and for your time. And if you have any further questions, don't hesitate to just send me an email and get in touch. Be happy to discuss that with you also after the lecture. Thank you very much.
Amazing. Thank you, guys, and see you all next week. Bye-bye.
Yeah, thank you. Bye.